GatedVAEs. Let's give them a big hand and take it away.
Cool, thank you. GatedVAE is the name of the work that I'm going to take you through, but I'm going to spend a little bit of time before I go through that talking about disentanglement, why it's important, why we might want to achieve it, and the challenges associated with achieving it. Just before I start, if you're interested in VAEs, it's one of the few talks about VAEs apparently, I've collated a list of sort of relevant research and recent papers in the field of VAEs, so if you want to check that out, I'm hoping it's going to be a useful resource for people who are working on these problems. So I'll start off by talking about what disentanglement is. There's a really wordy but concise at the same time, just laconic would be the word, definition of what disentanglement is recently from the DeepMind group. I'm not going to read it out. I'll probably trip over my own tongue, but I will say it's got words like symmetry group, independent subspaces and subgroups, so I just want to elaborate on those a little bit. And I'm going to elaborate it with my friend here, the apple. So imagine if I have an apple, and I can translate that into different positions in 3D space, but I can also rotate it. They're known as symmetry groups. It's a term borrowed from physics. And it'd be really nice if we could start to learn representations that allowed us to disentangle these generative factors in a way that allows us to give a sort of independent control over them. Initial definitions were quite sort of, I guess, blunt in the sense that they were just seeking statistical independence between individual dimensions. So like a factorized Gaussian, it doesn't really matter what it is, but statistical independence between independent dimensions is not enough when you're dealing with subgroups and subspaces. So for instance, if you want to disentangle color, you at least want RGB or LSV, whatever it ends up disentangling. Same with rotation as well. You're dealing with these subgroups that exist rather than just independent dimensions. So I hope that sort of gives you some idea what disentangled representation is. Disentangled representation is essentially working out what the generative factors are and sort of decomposing them into sort of independent subgroups. So why is it useful? Well, it moves us towards causal inference and latent modeling. This I personally feel is a really important direction for us to go in. In AI, at the moment, it feels like a little bit all we do is exploit correlations. And actually, if we're going to sort of generate understanding about the world and how the data is truly structured and interventions and how we can understand the process that led to it, then we're always going to be stuck at that sort of bottom rung of understanding. So I borrow that from sort of Judea Pearl, who I'm a big fan of. And yeah, I'm hoping that disentangled representations is sort of one sort of perspective relating to causal inference. So it's going to help us understand the data generation process. So even if we're not going down the causality route, if we achieve disentangled representations, we can interrogate them and try and sort of post hoc interpret them. It increases our predictive power quite often. You might think, well, I don't know really why that is, but anyone that's sort of compared, say, an output of a classifier to an output of a classifier then tagged on a SVM will see that there are various ways to extract information and leverage information in data, but if they're disentangled, we'll find that it's much easier to leverage that information. And also, we're talking about generation of data here, so it allows for independent control of these generative factors. So when we tweak a dimension or a subgroup, we want to be able to control that in a way that's intuitive and semantic, and not just some weird entangled mush of sort of different factors. A lot of the stuff we're talking about today is unsupervised, or at least has sort of unsupervised roots. Unfortunately, it's impossible to do disentanglement in a way that we want. So Diane Whip sort of talks about this, as well as Locatello in a more empirical sense. But this is the original definition of disentanglement, which is just that statistical independence. Your joint is the product of marginals. And this example sort of demonstrates why it's difficult to achieve. So imagine you had men and women. So we've got M and F, and they're old and young, Y and O. This would represent a nice disentangled representation where you have two dimensions. One dimension corresponds with age, the other one corresponds with gender or biological sex. And you can see that's great. That's how we sort of intuitively do it ourselves. We just increment this dimension if we want to change them from old to young or vice versa. So. But unfortunately, we can achieve unique solutions that may achieve certain statistical properties that we use when we're trying to train our networks. But we might end up with something like this. This reminds me a little bit of the Huffman coding thing. You might achieve these unique codes for certain combinations or observations, but it doesn't really correspond with our semantic understanding of how the world works and how we should be disentangling. So unfortunately, we're going to need a little bit more help to achieve what we want to achieve if we're going to do it at all. So I'm going to talk a little bit about how we evaluate disentanglement, then I'm going to have a brief review of VAEs. We actually haven't had that much of it today, so it leaves me a little bit to talk about, I suppose. Approaches to disentanglement, and then I'll talk about our approach finally. So one way to do it, there's loads of these quantitative metrics for disentanglement. These sort of they kind of orbit around the idea of mutual information or statistical independence. The ones that we've chosen to use are these, the Eastwood and Williams metrics that have been reviewed a number of times, actually in sort of meta-reviews subsequently, and they've been shown to sort of correlate well with the others, as well as sometimes correlate well with our subjective expectations. But again, it's kind of like it's hard to achieve in an unsupervised way. So we're going to be coming back to these briefly as our ways of doing it objectively. You can also evaluate it qualitatively. So here's traversals in the latent space. So we're just tweaking the value of a particular dimension and seeing the corresponding change in the output. And what you can kind of see is that this is the head pose partition. You can see variance in head pose here. These are dead latents. They've been subject to latent collapse or KL varnishing. And then over this side, you've got the expression and appearance here. So you see there's a smile dimension here. And so we can certainly like come in post hoc and evaluate the disentanglement, but it'd be nice to be able to do it without having to come in afterwards. So, brief overview of VAEs. It's an explicit density method, which is great, as opposed to an implicit density method. So GANs are implicit, you have no way to evaluate the likelihood. But I mean, I say it's explicit, we're still dealing with a proxy here. We don't have a really like robust estimation of well, in this case would be a conditional likelihood. But we have at least a proxy for it, so we can try and train on that. This is the probabilistic graphical model corresponding with the VAE. So the idea is you have observations, we have some latent generative factors Z that are unobserved. We're trying to infer these using parameters phi, and we're trying to generate from them our original data, theta. So I find PGMs quite useful for communicating a lot of information in a small space. Took a bit more space to do the full VAE, which is actually surprising because it's not that complicated, but sampling from a data distribution P of x, we're encoding it into a latent vector. In this case, if we're assuming Gaussianity, then we might go for a parameterization mu and sigma. We use the reparameterization trick, inject noise, multiply it to scale the variance, shift it to get the same mean. And then we draw our sample from that distribution. And then we try and reconstruct the original image. So going back to disentanglement, VAEs are quite often used to talk about disentanglement and to try and achieve it. There are various proposals that modify the VAE objective, such as putting mutual information regularization on it, trying to sort of decompose our latent space into these individual independent subspaces. But what Locatello found in his big meta-analysis, meta-review, was that the results tend to vary as much by random seed and random initialization as they do by the choice of objective function, which is, I suppose, quite a disappointing finding for the previous researchers in hindsight, potentially, I don't know. We have adversarial options. I'm not personally a big fan of adversarial training. It's quite difficult to do consistently, and you still probably need some supervision there in order to sort of play off information. But given that we need supervision, then we have three options. In this case, full supervision, semi-supervision, or weak supervision. We wanted to achieve disentanglement with as little supervision as possible, so we opted for weak supervision. And this could even be anything as weak as sort of domain knowledge. So imagine you had your data and you collected it. There might be natural clusterings in that data. For instance, you might collect images of men and women separately. That would be something that you already have access to. Anything that you can kind of extract, there was the hollow GAN, incorporating that inductive bias associated with 3D information. So anything that we can leverage here to start pairing up or seeing clusters in our data would be useful to us. So this is GatedVAE. Might look complicated. That's on purpose. It's not that complicated. This is literally just a dense network for the initial evaluations. We changed it to convolutional afterwards. This is a VAE, so we're passing images in. Here's the latent reparameterization in mu of sigma, reparameterization here, and then the latent sample, decoding it, and then reconstructing the image. The idea with GatedVAE is two things, I guess. first of all, we're going to gate the back propagation selectively. And the second thing is we're going to start pairing up images in a certain way. So I'll just take you through a training instance. We might pick an image, XA1, just select that at random. And then we're going to pick or pair an image that's not identical. So this deviates slightly from the auto-encoding nature because we're not pairing up the identical image at the input and the output. But we're going to choose this XB1 according to some shared factor that we have access to. So again, if your data is already clustered in some way, you might pick two images that are both men or two images that are both women. And we'd form a batch based on those pairings. So we'd have image, input image, man, output image man, input image woman, output image woman. That would be one batch. When we're training over that batch, we backpropagate gradients through the partition that we want to learn gender, that domain knowledge that we have access to. So if Z1 was, say, gender or biological sex, then we might want to backpropagate through this and then leave these untouched so these don't get trained. Then if we have another factor that we want to disentangle according to, say, age, then we can start pairing up images according to different ages, shared ages at the input and output, but varying across the batch, and then we backpropagate through the different ones. So we're gating gradients everywhere else and backpropagating through the partitions that we actually want to learn that factor. So again, it differs slightly from the auto-encoding principle because we're using different images, but yeah, it seems to work. So synthetic data set first, just varied in 3 factors, just to, I guess, sanity check everything's working. And one of the useful ways to visualize the output of the DCI, the disentanglement, completeness, and informative metrics, is using Hinton diagrams. So this was our result on the right, gated. Ground truth factors are here, so X position, Y position, and radius. Our inferred latent dimensions are here. And all we're saying is, can we predict independently the ground truth factors from the factors that we've learned? So this is actually textbook. I don't know if there are any textbooks on this, but if there were, that would be a textbook example of a disentangled sort of representation in the sense that we're using an inferred factor to predict X position, one inferred factor to predict Y position, one inferred factor to predict radius here. So you get a nice diagonal pattern. If there's entanglement, you get this a bit more messy. The network sort of assigned the variables as it sort of wants to arbitrarily, and every time I would run this training, I'd get a different form of entanglement. It looks slightly different each time. So step up the complexity using D-sprites data sets. So now we have shape, size, rotation, as well as X position and Y position as a sample from the data set. And this is a table that represents all of the results, disentanglement, completeness, and uninformativeness. They're sort of inverse. Essentially, one of the nice things about gated is that it doesn't just allow you to disentangle information, it also increases the informativeness. So you might think, well, this pairing is just going to allow me to put the information in a certain place. Actually also amplifies the amount of information in there. So we got the best results compared with all these other methods that are also unsupervised, InfoVAE, DIPVAE2, which have their various objective mods to encourage certain behaviors. So here's the visualization of those results, essentially. Gated versions boxed. And unfortunately, when we trained this, we were using that dense network. It's not a very powerful network. Rotation wasn't well encoded by any of them, so you get this rotation sort of spread across all the latent factors, but then the others were clearly disentangled according to a sort of consistent pattern with GatedVAE, as opposed to the others which are just sort of a mush. The information's there. It might not be as encoded as powerfully, but it's there. It's just sort of entangled across all latents. So finally, wanted to use Celeb A, this data set of faces. We extract the faces and make them grayscale just for efficiency. We don't have access to ground truth factors for this, the ones we wanted to pair on. So for evaluation, we went to qualitative evaluation. We paired the images up according to weak clusters on same head pose, same expression. So there's a lot of noise in the data there. That's why we term it weak supervision. But the results, which you've seen before, were actually exactly as we had hoped. So we got head pose partition of the latent space here. We gave it 6 dimensions. It only needed 3, actually only needs 2. So they actually decided to utilize the latent space by sort of not encoding, say, the yaw of the head all in 1 dimension, but split it over 2. Then there's a pitch here as well. These are unused, and then these are all the rest, essentially expression and appearance. So the advantage of this is that I can just pull this latent partition out and use it to predict head pose, or I can pull this out, and you'd hope that the sort of predictions are then invariant to things like head pose and just useful for expression. Yeah, that is it. Thanks for your time.